Have you ever really thought about what a single atom looks like? I mean, really looks like. Today, we're going to dive into something that honestly sounds like it's straight out of science fiction. How in the world scientists actually manage to take a photograph of one. It's an amazing journey that all starts with a very simple but very tricky question.
Right? I mean, we live in this age of 4K, 8K, Ultra HD color, so why does this incredible, groundbreaking image look like it was taken 100 years ago? Well, the answer to that question reveals the unbelievable ingenuity it took to even capture it at all. And trust me, it has absolutely nothing to do with the quality of the camera.
So, to get why this is such a big deal, you first have to understand why taking a picture of an atom using our normal logic should be completely and utterly impossible. It basically breaks the most fundamental rules of how we see, well, anything.
Just think about how you're seeing this screen right now. Light is hitting it, and different wavelengths of that light are bouncing off and traveling into your eyes. The color of your shirt, the sky, a car, it's all just about which wavelengths of light bounce off an object and which ones get absorbed. That's the core principle behind all sight and all photography. Simple enough, right?
Okay, so if we see things because light bounces off of them, why can't we just build a ridiculously powerful microscope and just zoom in on an atom? Well, this is where we smash headfirst into a fundamental wall of physics. The problem isn't our lens, the problem is the light itself.
Now take a look at this. The difference in scale here is just mind-boggling. A single atom is literally thousands of times smaller than the wavelength of the visible light we used to see. Trying to see an atom with visible light? It's like trying to figure out the shape of a single grain of sand by poking it with a giant beach ball. The tool is just way, way too big for the job. And this slide shows you exactly what happens because of that. When a big light wave hits a big object, like a baseball, it bounces off. It reflects, no problem. But when that same light wave comes across something as ridiculously tiny as an atom, it doesn't bounce back. The wave just kind of beds around it and keeps going. It's a cool phenomenon called diffraction. The light wave, for all practical purposes, doesn't even know the atom is there.
Okay, so this is the logical next question, isn't it? If the problem is that our waves are too long, then just use a wave that's way shorter. Gamma rays have these super tiny wavelengths, totally small enough to interact with an atom. So, problem solved?
Not so fast. Here's the catch. The trade-off for getting that incredibly short wavelength is a huge amount of energy. Hitting an atom with a gamma ray isn't like shining a flashlight on it. It's like hitting it with a cannonball. You would either completely obliterate the atom or you'd knock it so far away you'd never see it. So you see the problem? Visible light is too big and gamma rays are way too powerful. We're stuck. So, if light in any of its forms just can't work, how on earth did anyone ever take that picture? Well, the answer forced scientists to get creative and turn to a completely different tool, one that plays by the very strange but very wonderful rules of quantum mechanics.
This was the central puzzle that had everyone stumped. To see something that's basically unseeable, you can't use the rules of our everyday visible world. You need something that can be both incredibly small and surprisingly gentle at the very same time. And the answer is one of the fundamental pieces of the atom itself.
The electron. Yep, the very same particle that's orbiting the nucleus of the atom we're trying to see is actually the key to seeing it. But wait a minute. An electron is a particle, right? A tiny little speck of matter. It's not a wave of light. So how could you possibly use it to take a picture?
And this is where things get really cool, and honestly a little weird. In the quantum world, things aren't always what they seem. These tiny subatomic particles, like our friendly electron, have what's called a dual nature. Sometimes they act like a solid little particle, sure, but when they're moving really, really fast, they also start acting like a wave.
And here is the real game changer. Unlike a photon of light whose wavelength is fixed, we can actually tune an electron's wavelength. It's wild. By changing how fast it's moving, we change its wavelength. We can speed it up just enough to get a wavelength that's tiny enough to interact with an atom, but, and this is the key, without giving it so much energy that it destroys the atom. We basically created the perfect adjustable microscopic probe.
So we've got our amazing new tool, the electron. But how do we actually harness this bizarre quantum property to create a real image? Well, that's the job of a truly remarkable piece of technology, the electron microscope.
Okay, so let's walk through this. First, you take some electrons and you use a super strong electric field to blast them up to incredible speeds. That gives them that perfect, tiny little wavelength we need. Next, instead of using glass lenses like a normal microscope, you use powerful magnetic fields, electromagnetic lenses, to focus that beam of electrons right onto your atomic sample. Now, as the beam hits the atom, some electrons get scattered or absorbed by it, but others pass right on through. And on the other side, there's a special screen that lights up wherever an electron hits it. What you get is a shadow, an imprint of the atom.
So, and this is the most important part, we aren't seeing reflected light at all. And that's why the image is in black and white. It's not a photograph in the way we usually think of one. It's a shadow map. It's actually a lot like a medical X-ray, you know? You see the dense bones in an X-ray because they block the rays and create a shadow. Well, here, the atom is blocking the electrons.
What an incredible achievement, right? But you know how it is in science. Every amazing answer just leads to a new, even tougher question. So if we can image an entire atom, can we just tweak the technology a bit and zoom in even further to see what's inside that tiny little nucleus?
I mean, the logic seems pretty solid, doesn't it? The nucleus is way smaller than the whole atom, so we'll need an even shorter wavelength. And to get that, we just need to accelerate our electrons to even crazier speeds. Seems simple enough. But this is where we run right back into that same old problem.
This quote from the research really just says it all perfectly. To get a wavelength small enough to actually resolve the nucleus, the electron has to be moving with such an insane amount of energy that the very instant it hits, it completely shatters the thing you're trying to look at. The act of observing destroys the object.
But here's the beautiful, unexpected twist in the story. Even though the scientists couldn't get a clean picture of the nucleus, they did something brilliant. They analyzed the debris from the collision. By studying the patterns of how these super high-energy electrons scattered after impact, they discovered something absolutely profound. The nucleus wasn't one solid little ball at all. Their destructive attempt revealed it was made of even smaller particles, protons and neutrons. And those were made of even tinier things called quarks. They failed to take the photo, but in doing so, they discovered the fundamental building blocks of pretty much all matter.
And that really just leaves us with a final fascinating thought. This whole adventure shows that sometimes the biggest discoveries aren't made by looking at something directly. They're made by cleverly interacting with it, even smashing into it, and then piecing together the story from the aftermath. It just makes you wonder what other secrets of the universe are out there waiting for us to find them, not through a lens, but through a collision.